CERN, the European Council for Nuclear Research, is home to the world's most powerful particle accelerator, the Large Hadron Collider. For decades, this sprawling complex has been the epicenter of groundbreaking scientific inquiry, unlocking the secrets of the universe. But what if you found out that amidst the pursuit of truth, CERN stumbled upon something so shocking, so inexplicable, that it sent shockwaves through the scientific community? What did they find that was so alarming? Join us as we unravel Switzerland's terrifying discovery at CERN before shutting it down. Inside CERN's Large Hadron Collider. CERN, the European Council for Nuclear Research, has been grabbing headlines since the 1950s with its bold experiments. But along with praise, it's also sparked worries about things like creating black holes or messing with reality itself. One of its biggest and most controversial feats? Building the Large Hadron Collider, LHC. The LHC might not be something you come across every day, so it's no surprise that many folks go through life without ever hearing about it. But here's the thing. This machine is like a time travel device, giving us a peek into the very fabric of the universe. It's a marvel of human innovation, a giant ring measuring 17 meters around and buried a whopping 175 meters beneath the Earth's surface. And get this, it's not just in one country. It stretches beneath both France and Switzerland, showing how teamwork can unlock the mysteries of the cosmos. This beast of a machine, with its $4.5 billion price tag, is the crown jewel of CERN's experiments. The building has swallowed up even more cash for upgrades and upkeep, and it's paid off big time, uncovering secrets of the universe. How does it work? Well, it's all about speed. The LHC whips particles around the loop until they're zooming near the speed of light, completing thousands of laps every second. How? With electromagnets so powerful they create a magnetic field 1,000 times stronger than Earth's own. But some worry about the impact of such a strong magnetic field on nearby electronics and our planet's magnetic balance. Once these particles hit their top speed, almost 1,000,000 times the speed of light, they slam into each other head-on, creating a powerful collision. It's like a cosmic crash. This collision releases a massive burst of energy and a whole bunch of different particles. When these particles collide, they shoot off in all directions, but they don't stick around for long. Most of them vanish in a flash. But here's where it gets really cool. By switching up the types of particles they send crashing into each other, scientists can uncover brand new particles hiding in the chaos. To catch these fleeting moments, they've set up super-sensitive detectors around the collision sites. These detectors act like cosmic cameras, capturing every detail of the collision. But all this action generates a mountain of data, over 15 petabytes every year. That's like a whole library of information. Sorting through it all takes a ton of time and effort, but within this data treasure trove lie the answers to some of the universe's biggest mysteries. Unraveling the Universe. One of the remarkable achievements of the LHC is shaking up the standard model. But why should you care about this model? Well, think of it as a guidebook for the universe, explaining how particles and forces interact, kind of like the instructions for building a Lego set. It covers everything from tiny particles like quarks and leptons to the forces that hold them together. Quarks, for instance, come in 6 different flavors, each with its own electric charge and mass. Then there are the leptons, such as electrons and muons, which play a crucial role in building atoms. And let's not forget about the bosons, the messengers of forces like electromagnetism and the glue that holds quarks together. But here's the twist. Despite its power, the standard model isn't perfect. It leaves some big questions unanswered. That's where the LHC steps in. With its mind-blowing collisions, it's uncovering mysteries that even the standard model can't explain. Take the beauty quark, for example. It's shaking up our understanding of the universe in ways we never imagined. Scientists made a surprising discovery. When beauty quarks break down, they don't follow the rules laid out by the standard model. According to predictions, these quarks should transform into muons and electrons at similar rates. However, experiments at the LHC showed something different. This unexpected twist suggests there might be unknown particles or forces at play, throwing a curveball at our understanding of the universe. And that's not all. The LHC's particle collisions sometimes produce bizarre particles that the standard model can't explain. Take the pentaquark, for example. It's a whole new kind of particle, made up of 5 quarks, instead of the usual 3 found in protons and neutrons. This discovery opens up a whole new realm of possibilities, hinting at other quark combinations waiting to be discovered. But what's really exciting is what this means for our understanding of the universe. The pentaquark hints at the existence of mysterious subatomic forces that we're only just beginning to grasp. It's like uncovering a hidden rulebook that's been guiding us all along, waiting for us to stumble upon it. The discovery of the pentaquark was mind-blowing. The statistical deviation was a whopping 15, showing just how precise and powerful the LHC really is. In the world of particle physics, hitting a deviation of 5 is the gold standard for proving a particle's existence, so 15 is beyond impressive. And it wasn't the only surprise. The LHC also uncovered the tetraquark, another exotic particle shaking up the standard model. This 4-quark wonder, named TCC+, adds a whole new layer to our understanding of particles. It's like a quartet of quarks, with 2 heavy charm quarks and 2 lighter ones, all bound together by the strong nuclear force. Just like the pentaquark, its discovery hints at even more quark combinations waiting to be found. But here's where it gets really interesting. TCC+ could help unlock the secrets of quantum chromodynamics, or QCDs. These are the rules that govern how quarks interact under extreme conditions, and they're a crucial part of the standard model. It's a complex puzzle, but studying QCD could lead to some groundbreaking discoveries about the fundamental nature of matter. The LHC detector played a key role in uncovering the tetraquark. Scientists caught a glimpse of the TCC+ signature amidst the chaos of proton collisions. But the TCC+ doesn't stick around for long. It's like a fleeting spark before it transforms into other particles. A revolution in particle physics. The LHC made a startling discovery. The Higgs boson, a particle crucial to our understanding of the universe, is heavier than we first thought. But what exactly is the Higgs boson? The Higgs boson, sometimes nicknamed the Higgs particle, is a tiny building block in the standard model of particle physics. It's born when the Higgs field, a fundamental field in particle physics theory, gets all stirred up through a process called quantum excitation. Now, in this model, the Higgs boson is a heavyweight champ. It's a type of particle called a scalar boson, with no spin, a positive charge, and no electric or color charges. But it's not very stable. It tends to break down into other particles pretty much as soon as it's born. But what's the deal with the Higgs field? Think of it as a cosmic carpet spread throughout the universe. This field has a special property. It always has a non-zero value, even in empty space. This gives mass to all sorts of particles, thanks to something called the Higgs mechanism. It's like the Higgs field throws a party and invites all the particles to join in, giving them their mass and breaking a cosmic symmetry in the process. And who do we have to thank for all this insight? None other than physicist Peter Higgs, who, along with a team of scientists, proposed the Higgs mechanism back in 1964. This groundbreaking theory helped explain how particles gain mass and led to the prediction of the Higgs boson. It was like putting together a puzzle. If their ideas were right, there had to be a particle out there with certain properties. And lo and behold, the Higgs boson came along to confirm it all. The Higgs boson is often called the God particle. After a 40-year-long hunt, scientists finally hit the jackpot in 2012. Using the powerful ATLAS and CMS experiments at the LHC in Switzerland, they discovered a tiny piece of the puzzle they'd been searching for, a particle that matched the long-sought-after properties of the Higgs boson. It was like finding the missing piece of a cosmic jigsaw puzzle. The discovery was so groundbreaking that two of the masterminds behind the theory, Peter Higgs and François Englert, were honored with the Nobel Prize in Physics in 2013. But while Higgs's name often gets all the credit, it's important to remember that this discovery was the result of years of hard work and collaboration among many scientists. In fact, between 1960 and 1972, several researchers independently contributed different pieces to the puzzle, laying the groundwork for what would eventually become known as the Higgs mechanism. Fast forward to recent times, after the LHC had more time to do its thing and collect more data. Scientists took a closer look at the Higgs boson and realized something surprising. Its mass is greater than 125 giga-electron volts per square speed of light. This discovery caused quite a stir, because if the Higgs boson is indeed heavier than predicted, it could mean rethinking the very foundations of our understanding of the universe. So, does this mean we need to toss out the standard model and start from scratch? Well, not necessarily, but it does hint at the possibility of new particles or forces lurking beyond our current understanding. It's like finding a whole new piece to the puzzle, one that could change the way we see the universe. Furthermore, the discovery of the heavier Higgs boson has sparked a fresh examination of the Higgs field and its significance in shaping the universe. The mysteries of the Higgs boson. Even after the discovery of the Higgs boson, research on this elusive particle continued. Looking ahead, the investigation into this elusive particle is set to deepen during the LHC's third cycle, especially after the completion of the particle accelerator's high luminosity upgrade in 2029. This upgrade will enable the LHC to conduct more collisions, providing researchers with increased opportunities to identify unusual phenomena that don't conform to the standard model. CERN estimates that with each yearly upgrade of the accelerator, it will produce a whopping 15 million of these particles, a significant increase from the 3 million Higgs bosons created in 2017. This abundance could help in distinguishing various flavors of the Higgs boson. Theories beyond the standard model of particle physics suggest the existence of up to 5 distinct forms of Higgs bosons, some of which may be less frequently produced than the fundamental Higgs. Even before these advancements, scientists have uncovered compelling evidence of a magnetic Higgs boson. But what makes the Higgs boson so important? The Higgs field plays a crucial role in shaping the universe, particularly in its early stages. It defines the properties of the vacuum in our space-time, giving rise to the existence of matter, interactions, and the emergence of mass in all fundamental particles. Without the Higgs field, and consequently the Higgs boson, the cosmos would lack atomic elements, stars, and even life itself. So why is the Higgs boson often referred to as the God particle? The nickname God particle gained popularity after the discovery of the Higgs boson. It is said to have originated from Nobel Prize-winning scientist Leon Lederman, who originally intended to refer to it as the goddamn particle due to its elusive nature. However, when publishing a book about the Higgs boson in the 1990s, the title was changed to The God Particle by the publishers. The interaction between the Higgs boson and religion has been a long-standing concern among modern physicists. However, the importance of the Higgs boson and the Higgs field cannot be overstated, as they are fundamental to the existence of mass in the universe. Without them, there would be no stars, planets, or even living beings, which partly explains why it's earned such a dramatic nickname. Beyond just characterizing the new particle accurately, scientists are intrigued by the Higgs boson for two main reasons. Firstly, they seek to understand how the physical vacuum, the space we inhabit, originated in the early universe. Secondly, they want to comprehend how this physical vacuum remains stable. The Higgs field is unique in that it imparts a non-zero mean expected potential energy to the physical vacuum, a factor that profoundly impacts our cosmos. Scientists believe that this energy potential is responsible for the existence of the electromagnetic force, which has an infinite range, and the weak force, which has a very limited range. To explore this further, scientists need to investigate how Higgs bosons interact with each other, requiring the creation of pairs of these particles. While the discovery of the Higgs boson has shed light on how other fundamental particles acquire mass, its own mass remains unexplained. The theory lacks a symmetry that would guarantee this mass and prevent unintended instability. Quantum fluctuations could potentially disrupt the physical vacuum itself, although this would occur on timescales much longer than the known lifespan of the universe. Nevertheless, scientists are searching for additional Higgs boson-like particles, which could indicate the presence of new physics necessary to stabilize the Higgs boson's mass. These considerations drive the need for further study, more data, and, if possible, access to higher collider energy. This ongoing effort, supported by hundreds of experts worldwide, demonstrates the enduring commitment to unraveling the mysteries of particle physics. Revealing hidden realms. The LHC has played a significant role in advancing the theory of extra dimensions, offering the potential to unveil realms beyond our familiar three-dimensional universe. So, what's the buzz about extra dimensions, and why are scientists so intrigued? Imagine if our universe, vast as it may seem, is just a fraction of what's out there. That's the essence of the theory of extra dimensions. It proposes that beyond the length, height, and width we're accustomed to, there could be additional dimensions. These dimensions are like hidden layers waiting to be uncovered. They might be tightly wound or minuscule, far too small for our current technology to detect. It's like viewing a thread from a distance. It seems one-dimensional, but up close, you see its depth and breadth. Similarly, these extra dimensions might be all around us, existing unnoticed due to their tiny scale. Why do scientists care about other dimensions when we've managed fine with just 3? Well, they're on a quest to unite the forces of nature. Remember how the standard model covers 3 of the 4 fundamental forces? Gravity, however, is the stubborn one. It's much weaker than the other forces, like electromagnetism and the nuclear forces, and fitting it into the standard model has been a puzzle for ages. But here's where extra dimensions come in handy. According to this theory, gravity might spread out into these hidden dimensions, explaining why it's so feeble compared to the others. And guess what? The LHC is crucial to exploring this idea by diving into the tiny world of particles. You've already heard about the LHC's knack for uncovering surprises, from unexpected particle collisions to the peculiar behavior of quarks. These findings hint that there might be phenomena in the universe that the standard model can't account for, but could be explained by the theory of extra dimensions. Take the Higgs boson, for instance. Its unexpected weight could be due to interactions with unknown particles or fields from these extra dimensions, causing the mass discrepancy we observed. Similarly, the mysterious speedy decay of beauty quarks might be influenced by forces or particles from these hidden dimensions. It's like peeling back layers of the universe to reveal its hidden secrets. Another fascinating aspect of the theory of extra dimensions is its potential to shed light on dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. Instead, we only know it exists because of its gravitational effects on visible matter. Scientists are thrilled about the theory of extra dimensions because it opens the door to the possibility of uncovering entirely new particles. These dimensions might hide novel particles and the forces that govern them, offering a glimpse into previously uncharted territory. And once again, the LHC plays a crucial role. This colossal machine can indirectly reveal these elusive particles and forces by analyzing the energy and momentum lost during particle collisions, and, as a bonus, confirming the existence of these particles and forces would provide validation for the theory itself. It's like peering into the unknown corners of the universe, uncovering secrets that have been hidden in plain sight. If you've heard of string theory, you'll understand why extra dimensions are so intriguing. In string theory, particles aren't tiny dots, but rather minuscule vibrating strings. These strings can exist in multiple dimensions, and to create the particles and forces we observe, they need to vibrate in at least 10 dimensions. So, the existence of extra dimensions is crucial for string theory to hold true. Now, how does the LHC come into play in detecting these extra dimensions? Well, one key aspect is its ability to track particle behavior at incredibly high energies. When particles collide at such energies, they break down into their fundamental components, revealing the underlying forces and how they interact. Scientists study the patterns of these interactions and decays to uncover clues about extra dimensions. Imagine we've successfully collided particles and obtained a flood of subatomic particles. If we only consider the known ions, the energy and momentum from the collision would be fully accounted for. However, if extra dimensions exist, some of this energy and momentum could escape into them. Scientists keep a close eye on this, as any missing energy and momentum could indicate the presence of extra dimensions. However, detecting these subtle discrepancies requires highly sensitive detectors capable of picking up even the slightest deviation from what's expected. It's like trying to catch a whisper in a crowded room, requiring precision instruments to pick up on the faintest signals. Another method scientists employ to uncover extra dimensions involves studying particle decay patterns. When certain particles decay, they transform into other particles in predictable ways, some of which adhere to the standard model. However, deviations from these predicted patterns can occur if unknown extra dimensions are at play. Therefore, scientists carefully analyze the decay patterns of particles, keeping an eye out for any deviations that could indicate the influence of extra dimensions. Another intriguing concept for observing extra dimensions and the role of gravity is the notion of micro black holes. Although micro black holes don't exist in reality, they can theoretically be generated during high-energy particle collisions, such as those occurring in the LHC. Some researchers speculate that micro black holes are more likely to form in a universe with extra dimensions. This hypothesis stems from the idea that while gravity is typically considered a weak force, it might exhibit greater strength in these additional dimensions. Thus, if black holes are detected during particle collisions, it could provide evidence for the existence of extra dimensions. Now it's time for today's subscriber pick. In the serene valleys of Switzerland, beneath the majestic Alps, CERN's Large Hadron Collider hummed with the promise of unlocking the universe's secrets. Yet, amid the relentless pursuit of knowledge, whispers began to echo within its labyrinthine halls. One fateful night, as physicists delved deeper into the realms of quantum mechanics, they stumbled upon an anomaly beyond comprehension. Particle collisions yielded results defying all known laws of physics. Terrifying energies surged, distorting reality itself. Fear gripped the scientific community as the implications became clear. CERN had breached the veil between dimensions. Unseen forces stirred, ancient and malevolent. Panic ensued as whispers of entities lurking in the shadows spread like wildfire. Switzerland, a custodian of CERN, faced a harrowing decision. With solemn resolve, the government ordered an immediate shutdown, sealing the facility's fate. Yet the horrors unleashed lingered in the collective consciousness, haunting dreams and sparking conspiracy theories. As the world struggled with the truth veiled behind bureaucratic silence, questions lingered in the air like a chilling fog. What lurked within the abyssal depths of CERN's experiments? And what was Switzerland's terrifying discovery at CERN before shutting it down? The implications of quantum entanglement. Quantum entanglement is one of the most intriguing mysteries in physics, blurring the boundaries between science fiction and reality. Imagine particles becoming so intimately connected that the state of one instantly affects the state of another, regardless of the distance between them. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, challenges our fundamental understanding of how the universe operates. The mind-boggling aspect of quantum entanglement is that it appears to defy the laws of classical physics, particularly Einstein's theory of relativity, which prohibits anything from traveling faster than light. When two particles become entangled, they seem to exchange information instantaneously, suggesting a form of communication that transcends space and time. However, despite its seemingly paradoxical nature, quantum entanglement does not violate the principles of relativity. Instead, it offers a fascinating glimpse into the mysterious world of quantum mechanics, where particles can exist in multiple states simultaneously and behave in ways that defy our everyday understanding of reality. CERN has a keen interest in exploring quantum entanglement, aiming to unlock new insights into the workings of the universe. By pushing the boundaries of quantum mechanics and delving into the intersection of quantum mechanics and general relativity, CERN hopes to uncover hidden truths about reality. Their scientists conduct experiments involving entangled particles, observing how these particles interact with each other across varying distances. Leveraging the precision of the LHC, researchers can measure the properties of entangled particles with unprecedented accuracy. Understanding quantum entanglement could revolutionize our comprehension of the cosmos. For instance, if particles can be entangled over vast distances, could this entanglement extend across time as well? Answering such questions could deepen our understanding of the flow of time. Moreover, exploring quantum entanglement may lead to discoveries of new dimensions. Certain characteristics of entangled particles hint at the existence of dimensions beyond our current perception. If entanglement indeed occurs across these dimensions, it could illuminate the structure of these hidden realms and how we might interact with them. Quantum entanglement isn't just a fancy idea in physics textbooks. It's a game changer for technology. Think about quantum computing, where entangled particles do computations that regular computers can't handle. This opens doors for cryptography, drug discovery, and other fields needing serious computing power. With secure communication channels that are practically unhackable, the possibilities are mind-blowing. But that's not all. CERN is diving into quantum entanglement to crack the secrets of not just black holes, but wormholes too. Yes, you heard it right. Wormholes, those hypothetical shortcuts through space and time. Imagine hopping into one and popping out near a distant star, like hitching a ride with the universe's Uber. Plus, we might soon have proof of parallel universes. Talk about mind-bending. Now, let's talk about supersymmetry, or SUSY for short. It's like adding an extra layer to the standard model of physics. SUSY says every particle has a twin with similar traits but different behaviors. Picture it like a mirror universe where every boson has a Fermion counterpart and vice versa. This theory could solve the mystery of dark matter, the invisible stuff that makes up a big chunk of the universe. SUSY particles might just be the missing pieces of the dark matter puzzle, with their stability, mass, and weak interactions lining up perfectly with what we know about them. It's like finding the last piece of the cosmic jigsaw puzzle. How does the LHC fit into the study of SUSY? It's all about the collisions. The LHC can recreate conditions similar to those right after the Big Bang, giving scientists a peek into the fundamental rules of nature. If SUSY particles are real, they could pop up during these collisions. SUSY also provides a handy framework for understanding extra dimensions. String theory, which SUSY is part of, needs these extra dimensions to make sense mathematically. SUSY helps keep these dimensions stable and suggests ways we might see their effects, like tweaking the strength of forces or the mass of particles, which is something the LHC can detect. It's like using a microscope to explore the hidden corners of the universe. Debunking conspiracy theories. Conspiracy theorists have spun various hypotheses about CERN's activities, but the most alarming suggests the organization is trying to open a portal to hell. They fear that CERN's experiments with subatomic particles at lightning speeds could lead humanity into the depths of inferno. However, CERN maintains that its goal in generating antimatter is to deepen our understanding of matter and mass. Antimatter, possessing the opposite electrical charge of matter, is rare and was likely formed during the universe's birth, according to the Big Bang theory. Another theory links CERN to the Mandela effect, a phenomenon where people recall past events differently. Some speculate that CERN's particle experiments might disrupt reality, causing a large-scale Mandela effect. Lastly, there's speculation of human sacrifice at CERN, fueled by a leaked video allegedly depicting ritual sacrifices. CERN has refuted this, labeling it as a hoax. Despite these theories, CERN's primary mission remains scientific exploration. Neutrinos, elusive subatomic particles, have recently been detected by the LHC. This breakthrough could provide insights into intense neutrino interactions, shedding light on stellar phenomena like supernovae. Neutrinos, often dubbed ghost particles, are everywhere yet nearly undetectable due to their elusive nature. Despite their prevalence, they rarely interact with matter, making them a fascinating subject of scientific inquiry since their discovery in 1956. In 2021, physicists stumbled upon the faint presence of 6 neutrinos, but it took them 2 years of meticulous research to confirm their existence. James Boyd, a particle physicist at CERN and co-spokesperson for Fair Ghost, highlights the unique role of particles in unraveling the mysteries of deep space. These high-energy neutrinos detected at the LHC offer invaluable insights into intriguing astrophysical phenomena. The scientific community is on edge, eagerly awaiting CERN's next breakthrough and the implications it holds for the future of scientific inquiry. What are your thoughts on CERN's experiments at the Large Hadron Collider? Let us know your opinion in the comments below.